Luke stands on the edge of a cliff 35 meters high and throws a stone into the water. He throws it with a velocity of 16 meters per second and at an angle of 30 degrees to the horizontal. Now, the first thing I'll mention is that we know if someone is standing that they're going to be more than 35 meters above the water, but there's no sort of extra information given to us. So, we'll keep this simple and just say that, all right, we're 35 meters above the water. So Luke's standing up here on the grass at the top of the cliff, and the water is below. This is 35 meters, and he throws from this point here. So let's think what's going to happen. We're going to go up, hit our maximum, then drop down. So this first bit should be symmetrical, right, until we're level with the cliff again, but then we keep going down into the water below. We've got our initial velocity of 16, or our initial speed, I should say, of 16 meters per second, and the angle to the horizontal, right? So let's put in our horizontal line coming out from the cliff. Our angle to the horizontal is 30 degrees in here. Jump over to Desmos quickly, and we can model that over here. So let's adjust our angle down to 30 degrees. Our velocity is 16 meters per second. And our height now, we're not starting down at the origin, right? We're not down here. We're starting up at 35 meters. All the way out there. Might have to zoom out a little bit more. Okay. So we've thrown from up there, and then we can see it drop down. So, good little clue. We can see that we should be landing at around 50 meters away from the base of the cliff. Right, our maximum height is, well, let's get a bit more accurate. Our maximum height looks to be around 38 meters or so 3 meters above the cliff top. And like I said, in this section just here, let's bring it back, in this section just here we can see we've got the symmetry, but then we keep dropping down into the water below. Okay, let's get back to our example. In part A, we need to find the vector for the stone's displacement in the form S is equal to AI plus BJ, and we're given that G is once again 10 meters per second. So let's start with that, and we'll go through this first bit relatively quickly this time. So there's our acceleration vector. Integrating, we get velocity. And when we integrate with respect to time, we get minus 10t plus some constant vector. Now when t equals 0, what's happening with the velocity initially? Well, the velocity vector has a horizontal component of v cos theta, and so for us that's 16 cos 30 degrees. And it has a vertical component of v sine theta, so 16 sine 30 degrees. Now we should recognize these as angles that are good for exact values. So cos of 30 degrees, that's root 3 on 2. And so when we multiply 16 by root 3 on 2, we just get 8 root 3. And sine of 30 degrees, well, that's just a half. And so 16 lots of a half just gives us 8. So this is our initial velocity vector, which means when we come back to this line here, and we substitute this vector in on the left-hand side, and t equals 0 on the right-hand side, we see that this constant, well, it's a vector, but c for constant of integration, is equal to 8 root 3I plus 8j, which means the vector at any point in time is given by, well, let's do the horizontal part, so 8 root 3I plus, and then in the vertical component, the j component, we have negative 10t from here plus the 8 from here. Okay, so there's our velocity vector at any point. Let's keep integrating because we are after the displacement vector. So the 8 root 3, that's just going to become 8 root 3t. And then this second part, the j component, well, we have minus 10t. So when we integrate that, we get minus 5t squared. Right, just double check that if you need by differentiating it, and we see we go back to negative 10t plus 8t. So that's the vertical component. Plus another constant, and so that we don't mix it up with the constant c, let's go with d.